Hey everyone, welcome back. I hope everyone is doing well. A little while ago, we had a video on loss functions in machine learning, and we talked a lot about if your model is going to output some score, whether that score is going to be used for a classification problem or a regression problem, what are different loss functions that you have available to you to see whether that score is any good in terms of how close it is to the real label. Now, those are very important loss functions, and I'll link that video below. But one thing we did not talk about in that video, and that is increasingly important in today's applications, is what if your model is not trying to output a single score, but rather take some object in the real world, in this video that's going to be pictures of people, and embed them into a space in some smart way. And that whole sentence is kind of vague, and that's exactly where this video and the next video comes in to mathematically define what does that vague sentence, where we embed stuff in the real world into some embedding space in a smart way, how do we do that? Which loss functions tell us whether we did that well or we're doing that poorly? Now, that's enough vagueness. Let's go ahead and talk about the real-world example we're going to be using today. And through that, we'll talk about the topic of this video, contrastive loss. This is really the first part of a two-part video. In the next one, we'll talk about another loss function that's trying to do a similar thing called triplet loss. But the example today, let's say you run a top secret lab. So here's the door to your top secret lab. Now, the work you're doing in this lab is so top secret that I can't even talk about it in this video. But it's so top secret that you want to make sure that random people are not able to enter your lab. Only authorized people are able to enter your lab. So in this small example, we'll say that A, B, and C are authorized people, the only authorized people who are able to enter your lab. Now, you want them to enter very easily, and so you hook up a webcam on top of your lab door right here, and that's going to scan the faces of people coming in. And if the face of somebody who's trying to enter the lab is similar enough to the database of faces of people who are allowed to enter the lab, then they'll just be let right in. If the face of someone trying to enter the lab is not similar enough to any of these authorized people's faces, then they will not be let into your lab. And that is the example for today. So now, making it a little bit more concrete, what we're going to do is take a, let's say, 100 pixel by 100 pixel picture of whoever is trying to enter the lab. Here we see that this is probably person B, just matching up face to face. And what we're going to want to do is train some kind of machine learning model M, which is going to take the information in that 100 by 100 pixel image, so all of these pixel values, and turn it into an n-dimensional vector, or more contextually appropriately called an n-dimensional embedding of this picture, of the picture of this person. And we want to do it in a smart way. Now, we'll talk about what that means mathematically, but you know we don't like to jump right into the math on this channel, so let's first talk about it verbally. What would it mean for a model to be doing a good job of embedding these pictures into this n-dimensional space? Well, it would mean we're satisfying two criteria. Criteria number one, the distance between x1 and x2 being the embeddings, being the n-dimensional embeddings of two images, the distance between those embeddings should be small if those two embeddings belong to the same person. So concretely, if we have some picture of person B and we have a different picture of person B, well, those are the same person. And if I go ahead and take the embeddings of those two pictures, learned by the model, and I compute the distance between them, that should be a small distance. And that intuitively makes sense because this is the same person. We want their embeddings for their images to end up in a very similar part of the embedding space. And that implies that the distance between those embeddings should be small. And now that other criteria is just the opposite of the first criteria. The distance between x1 and x2 should be large. That should be a very large distance if x1 and x2 belong to the pictures of two different people. So if I have this picture of person B and I have a corresponding different picture of person A, then the distance between those two embeddings for those two pictures should be big because those are not the same person. So ideally, what this sentence or these two criteria encode is that we want to learn some model who is going to generate these embeddings such that embeddings for the same person kind of cluster together in the same part of the embedding space, but that cluster should be far from a corresponding cluster of the embeddings of pictures of somebody else. So now that we have the verbal explanation here, now we're going to start transitioning into the math. How do we encode these wants? How do we encode these two wants into a mathematical loss function L? What loss function is going to encode these two wants? Now, we're going to take it step by step based on these two criteria. So let's work on the top criteria first because it's going to be slightly easier for us to talk about. And to do that, I want to introduce some variable y. Y is just going to be a binary variable. It's going to be 1 if x1 and x2 are embeddings for pictures belonging to the same person, and y is going to be 0 if they're embeddings for pictures belonging to different people. So just to help us do some bookkeeping. So case 1, which corresponds to this first criteria here, is y is equal to 1. These are embeddings corresponding to pictures for the same person. Now, the loss function in this case is going to be dead simple, and it's just going to be a fallback on loss functions we already know about, namely the square loss here. So in this case, if you have two embeddings belonging to pictures of the same person, we're going to say the loss function is just the distance between those two embeddings squared, the distance squared. And if I were to explain that math in a single sentence, it would just be, in this case, these are the same people, and so the closer that distance is, the better our model is doing. In the best case scenario, that distance would be 0 and we'd be admitting a 0 loss. And the embeddings in that case would literally be the same. They would just be on top of each other. Think more about that. We'll come back to that in a second, because if that feels a little strange, maybe that mathematically seems right, but something about having all the pictures for a given person just kind of collapse on a single point, if that seems strange to you, it seems strange to me as well, and we'll talk about that. If these embeddings are further apart, then the distance will be larger and our loss will get bigger and bigger and bigger with the square of that distance. So far so good. Now, it's a little bit more interesting to talk about the second case, where y is equal to 0, and that's what we're going to do on this sheet here. So the second case, y is equal to 0. Something that seems really logical to try, and I love just trying things that seem logical instead of going to whatever the accepted definition is. We'll get to that accepted definition, but if I was engineering this from scratch, I would just stick a negative sign in front of the distance in this case. And so I would get, if these are embeddings belonging to pictures of different people, then the closer that distance is, that's actually worse for me. And the further that distance is, that's actually good. I want the embeddings for those two people to be very far apart because these are not pictures of the same person. And so if I just stick a negative sign there, all should be well, right? Well, something really interesting happens in this case, because when you think about distances, the absolute lowest you can make a distance is going to be 0. The absolute biggest you can make a distance, well, there's not really a concept of that. You can just push these embeddings further and further apart into infinity, having infinite distance from each other. And that's exactly what this version of the loss function would try to do. If you have 2 points that are here and here, let's say, belonging to embeddings of pictures of different people, it'll say, well, that's great, but I could get an even lower loss function if I were to move them further apart. And then it would say, well, that's great, but I could just move them further apart. And so those embeddings are going to not converge and just get infinitely pulled further and further and further apart, even further than we really care to have them apart. It seems like there's some kind of cap to where if the embedding for one person and a different person are this far, that's probably good enough. I don't need to push them any further. But that's not what's being promoted by this loss function. So we don't want these things to go to infinity. That's going to lead to a lot of computational problems for us. And so we're going to try a different thing, which ends up being the actual term that's used in contrastive loss. But it's important to start here, because you have to know, why not do the simple thing before you go to something a little bit more complicated. So the little bit more complicated thing is that we're going to say our loss function is going to be positive. We're going to have a positive loss if and only if the distance between these two embeddings belonging to pictures of two different people is going to be less than some margin m. So m is some kind of margin. And that's exactly encoded in this math right here. So the first thing I want to do is just show that this sentence up here lines up with this math down here, and then I'll talk about the intuition, because this was the hardest part of contrastive loss for me to grasp. Once we grasp this, it'll be really simple. So first, let's make sure that this sentence lines up with this math. Is the loss only greater than 0 if and only if this distance is less than this margin m? Well, let's just go through the couple different cases we could have here. If this distance is less than m, then m minus d is going to be some kind of positive number. The maximum of 0 and some positive number is going to be that positive number, and we square it. And so the loss function is greater than 0 in that case. So at least part of this conditional is true so far. Now let's say the distance is greater than or equal to m. What happens in that case? Well, if the distance is greater than or equal to m, then this m minus d is going to be less than or equal to 0. The max of 0 and something less than or equal to 0 is going to be 0, and then therefore the loss is going to be 0. So if the distance is greater than or equal to m, then the loss is equal to 0. If the distance is less than m, then the loss is going to be greater than 0. So these two statements, one being mathematical and one being verbal, do line up exactly with each other. But more importantly, what are we actually trying to get at here in terms of solving the problem in the first try? Well, if I could just draw a little picture here, what we're saying is that if here is one embedding for, let's say, person A, and here's an embedding for person B. Now, if the distance between them is going to be something less than m, let's just say m is 1 in this case, so if the distance is less than 1, then we're going to have a positive loss, and the model is going to get promoted for bringing them further apart. So let's say we train the model a little bit more, and now this embedding for person B is out here. So let's say it's out here. And let's say that's going to be greater than m. So that's going to be greater than 1. The distance is now bigger than the margin that we have set. So if the distance is now bigger than the margin we've set, the loss is equal to 0, and the model no longer has any incentive to move this embedding for person B's picture any further than it currently is from the embedding for person A's picture. And that's exactly what we want. We don't want these two embeddings to get arbitrarily pushed out to infinity, which is what would happen in this case here. And so that's exactly how this second try, although looking a little bit more complicated than our first try, is going to actually fix that problem. It's just going to push these two embeddings far enough apart that we're comfortable with, and that level of comfort is literally decided in the definition of the margin m here. And so what that all means, putting together case 1 and case 2, is that our overall loss function is just going to be the sum of those two cases with this y and 1 minus y attached. And I'll show you why that y and 1 minus y is there. So it's going to be y times d squared. This came from our first case. And then 1 minus y times the max of 0, m minus d squared, which came from our second case. Now the reason we put this y and 1 minus y, pretty easy to see. Let's say we're dealing with a training example where y is equal to 1. Then this is going to just be reducing down to d squared because 1 minus y is 0 and this second term goes away. That's exactly what we want. Conversely, let's say we're dealing with a training example where y is equal to 0, then the first term goes away. This term here is just 1, and we just fall back on that second case. So this is kind of just a on-off switch, if you will, a mathematical on-off switch for which case we're in. And this, folks, is called contrastive loss. This is the definition of contrastive loss, and it is named so because we have mathematically engineered our loss function to contrast between examples of different classes. And what we end up with when we train a model who is trained on contrastive loss is, in the best case, something that looks like this. So here's person A, and these black dots here represent embeddings for images that are learned by the model for person A. Same thing with person B and person C. And we'll get to this person D in just a second, who is not allowed into the lab. But we see that all of the embeddings for person A, all of the embeddings for B, all of the embeddings for C have kind of clustered together. And that's from this first part of the loss function where we want the distance between these things to be very close together. But those clusters are far enough apart from each other. If we draw little circles of radius m around these examples, we have incentivized the model to learn not to put the embedding for C, for example, inside any of those circles. The embeddings for people who are different for a given person should have their embeddings always outside of those circles, always further than a distance m away from any of those embeddings. And so this also gives us an illustration of two things, two features that are going to be important for how we think about this model. One is, how do you actually now use this model to do anything? So let's say you now train this model using contrastive loss, and let's say that person A shows up to the lab and it takes that 100 by 100 pixel image of them. Now we have that model, it's going to embed that new visit for person A into the embedding space, and we'll say that new visit is right here. Now what we go ahead and do is compute the distance between that new visit and existing points that are in our embedding space, and we'll see that those are usually closer, as we had engineered the model to do via caring about contrastive loss. Those are usually closer to examples that belong to person A's pictures, and usually much further from examples that belong to other people's pictures. And we can use a threshold on those distances to say, this is very close to person A's pictures, this is probably person A. Person A is an authorized user, I'm going to go ahead and let them into the lab. Same thing if person B made another visit, same thing if person C made another visit. So A, B, and C are now allowed and able to enter the lab just by scanning their faces. Now, what happens if a rogue actor, someone who's trying to steal your top secret information, person D, shows up? Well, it's going to take a picture of them and embed them also in the same space. But remember, because contrastive loss has the second term, which says the embedding for two different people should be far away from each other, well, person A and D are not the same, C and D are not the same, B and D are not the same, so it should be sufficiently far from all of them, so that embedding ends up somewhere over here. And then when we do our distance calculation, it doesn't pass the threshold. It's not close enough to the threshold of any given picture that exists in our system. And therefore, this person gets rejected. This person gets rejected and they're not allowed to enter the lab. And that's how we would use contrastive loss to train a machine learning algorithm that is designed to embed real-world objects, in this case pictures of people, into an n-dimensional embedding space to actually achieve a goal, to actually achieve this facial recognition system. Now, one thing we need to do in this video is we talked about all the benefits and cool things of engineering this contrastive loss and what it's able to do, but we need to talk about the issues that can come from contrastive loss. And those issues are going to come from what we call hard negatives and hard positives. Let's start with hard negatives here. And to talk about that, let's consider an initial case where we have two embeddings for person A. Let's call them A1 and A2 to distinguish between them. And we also have an embedding for person C, which is currently beyond the margin when we're considering the training pair A1 and C. My question to you is, in this case, should the model move A2 closer to A1? Contrastive loss would definitely say, yeah, because that first part of the loss function d squared is going to be smaller and smaller if that distance gets closer and closer to 0. And so yeah, we'd want to move A2 closer to A1. Like we were hinting at earlier, that does make mathematical sense, but intuitively it does seem like a little bit weird to move all of the embeddings for a given person's pictures collapse to the same point in the embedding space, especially if the embeddings for other people's pictures are already far enough away, as we see with C and A1 here. Now, let's adjust the case a little bit and assume that person C showed up to work one day wearing an eye patch, which made it harder for the model to learn to put C's embedding far away from A1's embedding. We call such a case a hard negative, because it is hard for the model to consider A1 and C as negative examples. We assume here that no matter what we do, we have hit a point where we cannot move the embedding for A1 and C further apart. In this case, I'd ask the same question. Should we move the embedding for A2 closer to that of A1? Now, I think that many of us would agree that the answer should be yes, because otherwise we have A1 and C way too close together, and there is an actual advantage and incentive for moving the embedding A2 closer. This whole nuanced story, which we can only get by looking at these triplets of points, looking at 3 points at a time, is totally gone in contrastive loss, which only operates, remember, on pairs of points. In both cases, it's going to choose to move A2 closer to A1, regardless of this context, regardless of this nuanced story around embedding C. Now, in an opposite case, which actually stems from the same root cause, let's start with the same initial setup as before, but instead ask, is there any incentive for us to move embedding C further away from the embedding for A1 in this case? Well, contrastive loss would say no, because considering A1 and C is already outside the margin for A1, and so there's no benefit to moving it further. And hey, I'd actually agree here. I think that makes total sense. But let's again change the example a little bit and see if that still makes sense. We're going to change it by assuming that person A came to work one day copying person C's hairstyle because it was just so cool, but that had the side effect of making it harder for the model to consider A1 and A2 as pictures belonging to the same person because those pictures don't look so similar anymore. In this case, we call A1 and A2 hard positives because it's hard for the model to consider them as positive examples. In this case, we literally cannot move A1 and A2 any closer together. Same question now. Would we want to move C further away? Well, contrastive loss would still say no when we're considering A1 and C because of the same margin logic we just talked about. But looking at the richer context of the triplet A1, A2, and C all together, I'd actually argue that we do want to move C further away in this case, because doing so is going to implicitly make it look like A1 and A2 are more similar, because their distances will be relatively smaller when we move C further away from A1. That whole nuance story is also lost when we use contrastive loss. In both cases, it's going to refuse to move C any further away from A1, regardless of the story going on with A2. So in both cases, the story is that we lose something important by just looking at pairs of examples, which we could and should arguably take advantage of by looking at triplets of examples. And folks, that is exactly the guiding philosophy behind using triplet loss, which is what we're going to explore in the next video. And I think that's a pretty good place to end this video. So hopefully in this video you learned about what the contrastive loss is and why it helps us smartly embed things in the real world into an embedding space in a very natural way. So if you like this video, please like and subscribe for more videos just like this. Any and all comments are welcome in the section below, and I'll catch all you wonderful people next time.